Ocean and tidal energy. Harnessing the power of the sea. Course content. Introduction to ocean and tidal energy. The science behind ocean energy. Types of ocean energy. Tidal energy, principles and technologies. Wave energy, mechanisms and devices. Ocean thermal energy conversion, OTEC. Salinity, gradient energy. Environmental impacts. Economic viability. Policies and regulations. Integration of ocean energy into the power grid. Case studies. Future trends. Conclusion and recommendations. Part 1. Introduction to ocean and tidal energy. The ocean, a vast source of renewable energy. The Earth's oceans cover more than 70% of the planet's surface and hold immense potential as a renewable energy source. Unlike terrestrial sources, the ocean offers a variety of energy forms: tidal movements, wave actions, thermal gradients, and salinity differentials that can be harnessed to produce electricity sustainably. As the world searches for cleaner energy alternatives, ocean and tidal energy have emerged as promising options in the pursuit of carbon neutrality and energy diversification. Understanding ocean and tidal energy. Ocean energy refers to all the energy derived from the movement and physical characteristics of the sea, while tidal energy is a subset specifically generated from the rise and fall of tides. These phenomena are predictable and consistent, offering a level of reliability that other renewable sources like solar and wind may lack. The main forms of ocean energy include tidal energy, energy generated from the gravitational interactions between the Earth, Moon, and Sun that cause tides. Wave energy, energy from surface waves caused by wind blowing across the sea surface. Ocean thermal energy conversion, OTEC, utilizes the temperature difference between surface water and deep water. Salinity gradient energy, generated from the difference in salt concentration where freshwater rivers meet the sea. Historical context and evolution. The idea of harnessing ocean energy is not new. The use of tidal mills dates back to the Middle Ages. However, technological constraints limited its expansion. In the 20th and 21st centuries, advancements in engineering, environmental awareness, and the need for energy security have reignited interest in ocean and tidal energy. Notable milestones include the opening of the Rance tidal power station in France in 1966, the world's first large-scale tidal power plant. The development of various wave energy prototypes in countries like the UK, Portugal, and Australia. The growing number of OTEC pilot projects in tropical regions. Why ocean and tidal energy matter today. The urgency to transition to clean energy sources has never been greater. Ocean and tidal energy offer several distinct advantages. Predictability. Tidal movements follow lunar cycles and can be forecasted with high accuracy. Low carbon footprint. Once operational, ocean energy systems emit little to no greenhouse gases. Energy security. Utilizing local marine resources reduces dependence on imported fuels. Potential for high energy output, particularly in coastal nations with strong tidal flows or wave activity. Key players and global outlook. Countries with extensive coastlines and supportive policies are leading the way in ocean energy development. These include United Kingdom, a global leader in tidal stream and wave energy technologies. France and South Korea, investing heavily in tidal range projects. United States and Canada, supporting pilot projects through governmental grants. China and Japan, exploring integrated marine energy systems. International organizations like the International Renewable Energy Agency, IRENA, and the Ocean Energy Systems, OES, of the International Energy Agency are playing pivotal roles in research collaboration and policy development. Parts summary. Ocean and tidal energy represent an exciting frontier in renewable energy. With vast potential, particularly for island nations and coastal regions, this form of energy could contribute significantly to a diversified and resilient energy future. As technological and economic barriers are gradually addressed, ocean energy is poised to play a vital role in global sustainability goals. Part 2. The science behind ocean energy. Fundamental oceanographic principles. To understand how energy can be harnessed from the ocean, it is essential to grasp some basic principles of oceanography, the study of the ocean's physical and dynamic processes. The movement and characteristics of ocean water are influenced by a combination of gravitational forces, wind patterns, temperature differentials, salinity levels, and the Earth's rotation. Key drivers include gravitational pull of the Moon and Sun, primary cause of tides. Wind friction over the ocean surface generates waves. Thermal stratification drives ocean thermal gradients. Density differences due to salinity create pressure gradients that can be harnessed. Tidal movements. Tides are the periodic rise and fall of sea levels caused by the gravitational interactions between the Earth, the Moon, and the Sun. There are two main types of tides. Spring tides occur when the Sun and Moon align, resulting in the highest tidal ranges. Neap tides occur when the Sun and Moon are at right angles, leading to minimal tidal variation. Tides occur predictably, typically twice a day semi-diurnal or once a day diurnal, depending on the geographical location. The regularity of tides makes them a reliable source for energy production. Ocean waves and energy transfer. Waves are primarily created by wind blowing over the surface of the sea. The size and energy of waves depend on wind speed, wind duration, fetch, the distance over which the wind blows. Energy is transferred from the wind to the water, causing oscillatory motion. The energy contained in a wave is proportional to the square of its height, making high consistent waves particularly valuable for energy generation. Ocean thermal energy. The surface layers of the ocean are warmed by solar radiation, while deeper layers remain much cooler. This temperature difference can be as high as 20 degrees Celsius in tropical regions. Ocean thermal energy conversion, OTEC, exploits this thermal gradient using a heat engine to generate electricity. Key thermodynamic concepts involved. Heat exchangers transfer thermal energy between fluids. Working fluids with low boiling points, like ammonia, are used to drive turbines. Rankine cycle or similar closed-cycle systems are typically employed. Salinity gradients and osmotic power. When freshwater from rivers meets salty seawater in estuaries, the difference in salt concentration creates a pressure gradient. This natural osmotic process can be harnessed to generate energy using pressure-retarded osmosis (PRO), reverse electrodialysis (RED). These technologies are still in development, but hold promise due to their continuous and renewable nature. Energy density and conversion potential. Ocean energy resources are among the most energy-dense forms of renewable energy. Consider the following. Wave energy. Average global wave power density ranges from 10 to 60 kilowatts per meter of wavefront. Tidal energy can reach power densities of up to 10 kilowatts per square meter in areas with strong tidal currents. OTEC has a lower efficiency, -3 to 5%, but can operate continuously. Salinity gradient offers an estimated global potential of 2,000 terawatt-hours per year. Technological implications of marine conditions. The ocean is a challenging environment for energy systems due to corrosion from saltwater, biofouling, marine organisms growing on equipment, extreme weather conditions, maintenance difficulties in remote locations. Therefore, technologies must be robust, corrosion-resistant, and capable of withstanding harsh marine environments. Parts summary. The science behind ocean energy is rooted in natural processes that are continuous, predictable, and globally available. From gravitational tides and wind-driven waves to thermal and salinity gradients, these forces provide diverse pathways for sustainable energy production. Understanding the physical principles involved is essential for developing efficient and reliable ocean energy technologies. Part 3. Types of ocean energy. Ocean energy encompasses a wide range of renewable energy forms derived from various physical and chemical characteristics of the ocean. Each type has unique mechanisms for energy extraction, infrastructure requirements, and levels of technological maturity. This part explores the primary types of ocean energy in detail. Tidal energy. Tidal energy is generated from the predictable rise and fall of sea levels caused by gravitational interactions among the Earth, Moon, and Sun. There are two main methods to harness tidal energy. A. Tidal range energy. This involves capturing the potential energy created by the height difference between high and low tides. Tidal barrages function like dams across estuaries, allowing water to flow through turbines during tidal changes. Key example: Reims Tidal Power Station, France. Advantages: high predictability, capable of generating large quantities of electricity. Challenges: high capital cost, potential environmental impact on estuarine ecosystems. B. Tidal stream energy. This method captures the kinetic energy of moving water as tides flow through coastal areas or between landmasses. Devices are often submerged turbines similar to underwater wind turbines. Suitable for areas with strong tidal currents. Advantages: less intrusive to ecosystems than barrages. Can be scaled more easily. Challenges: marine biofouling, maintenance in harsh underwater environments. Wave energy. Wave energy is derived from surface waves generated by wind. The amount of energy a wave carries depends on its height, period, and length. Wave energy conversion devices. Point absorbers float in all directions using up and down motion to generate power. Oscillating water columns trap air that is pushed by incoming waves driving air turbines. Overtopping devices capture water from waves into a reservoir, releasing it through turbines. Advantages: high energy density in consistent wave regions. Potential for integration with coastal infrastructure. Challenges: variability in wave conditions. Need for durable materials to withstand marine forces. Ocean thermal energy conversion, OTEC. OTEC takes advantage of the temperature difference between warm surface seawater and cold deep seawater in tropical oceans. It uses this thermal gradient to run a heat engine. Types of OTEC systems. Closed cycle uses a working fluid with a low boiling point, e.g. ammonia. Open cycle, seawater itself is used to generate steam. Hybrid cycle combines both open and closed systems. Advantages: continuous operation, base load power. Potential for co-products such as freshwater and cooling. Challenges: low thermal efficiency, -3 to 5%. High infrastructure cost and maintenance. Salinity gradient energy. Salinity gradient energy, also known as blue energy, exploits the chemical potential between freshwater and saltwater. Two main technologies. Pressure-retarded osmosis (PRO) uses osmotic pressure to generate mechanical energy. Reverse electrodialysis (RED) uses ion exchange membranes to create voltage from salt concentration differences. Advantages: steady energy source at river mouths. Minimal visual and noise pollution. Challenges: membrane efficiency and fouling. Technology is still in early stages of commercialization. Hybrid and emerging ocean energy concepts. Some systems combine multiple ocean energy types or integrate them with other renewables. Examples include floating platforms with solar panels and wave energy converters, multi-source marine energy parks with tidal, wind, and wave devices, subsea energy storage systems powered by ocean energy. These integrated systems offer higher reliability and optimize space in offshore environments. Global potential and resource distribution. The potential for ocean energy varies by region. Tidal energy is strongest in places like the UK, Canada, South Korea, and parts of France. Wave energy is prominent in western coastal regions such as Portugal, Scotland, and Australia. OTEC is best suited for equatorial and tropical regions. Salinity gradient is feasible in estuaries worldwide, especially in river-rich countries. Parts summary. Ocean energy can be tapped in multiple forms, from the rhythmic pull of tides to the continuous swell of waves and subtle gradients in temperature and salinity. Each type offers specific advantages and faces unique technical challenges. Understanding these categories sets the foundation for exploring the technologies used to harness them, which we will delve into in the next part. Part 4: Tidal Energy Principles and Technologies. Tidal energy is one of the most predictable and reliable forms of renewable energy, driven by the natural gravitational forces of the Moon and the Sun. This part explores the principles behind tidal energy, the technologies used to harness it, and the practical considerations for its implementation. The physics of tides. Tides are caused by the gravitational pull of the Moon and Sun on Earth's oceans, combined with the Earth's rotation. These forces lead to the periodic rise and fall of sea levels, generally occurring in cycles of approximately 12.5 hours. There are two main types of tides. Semi-diurnal, 2 high tides and 2 low tides each day, e.g. Atlantic coasts. Diurnal, 1 high tide and 1 low tide each day, e.g. Gulf of Mexico. Tidal energy exploits either the potential energy in the height difference, tidal range, or the kinetic energy in the flowing water, tidal stream. Tidal range energy. Tidal range energy systems capture the potential energy created when there is a significant height difference between high tide and low tide. Tidal barrages. These are large dams built across estuaries. Gates and turbines control water flow between the sea and a basin. How it works. At high tide, gates open to fill the basin. As the tide recedes, the gates close, and water is released through turbines to generate electricity. Pros: high power output, predictable energy generation. Cons: expensive infrastructure, potential environmental impacts on estuarine ecosystems. Tidal lagoons. Similar to barrages but built along the coastline rather than across estuaries, enclosing part of the sea. Example: proposed Swansea Bay Tidal Lagoon, UK. Tidal stream energy. Tidal stream systems use underwater turbines to capture the kinetic energy of moving water. These systems are comparable to underwater wind turbines and are suited to coastal areas with strong tidal currents. Types of tidal stream devices. Horizontal axis turbines. Rotors turn parallel to the tidal flow. Vertical axis turbines. Rotors spin perpendicular to the flow. Oscillating hydrofoils. Move up and down with the current to drive a hydraulic system. Venturi effect turbines. Use funnel-shaped structures to increase flow speed through the turbine. Pros: minimal visual impact, scalable and modular, low operational emissions. Cons: harsh underwater conditions complicate maintenance, potential interference with marine life and navigation. Site selection criteria. Optimal tidal energy sites must meet specific criteria. High tidal range or strong tidal currents. Proximity to shore to minimize transmission losses. Minimal environmental sensitivity to reduce impact. Bathymetric and geological suitability for construction. Examples of ideal locations. The Severn Estuary, UK. Bay of Fundy, Canada. Jeollanam-do Province, South Korea. Environmental considerations. Tidal projects, particularly barrages and lagoons, can have significant ecological impacts. Habitat disruption for estuarine and marine species. Changes in sediment transport and water quality. Noise and vibration affecting aquatic organisms. Modern designs aim to reduce these effects using fish-friendly turbines. Adaptive management strategies. Ongoing environmental monitoring. Key projects and technologies. Several landmark projects and commercial devices demonstrate tidal energy's feasibility. Rance Tidal Power Station, France. Operational since 1966. 240 megawatts capacity using a tidal barrage. Siwa Lake Tidal Power Station, South Korea. World's largest operational tidal power station. Uses an existing seawall to generate 254 megawatts. Maygen Project, Scotland. Tidal Stream Project in the Pentland Firth. Uses underwater turbines to produce grid-connected electricity. Technological innovations. Modern tidal energy is evolving with advancements such as floating tidal platforms for deep water deployment. Modular turbine arrays for cost-effective scaling. Hybrid tidal wind systems for offshore energy parks. Smart monitoring systems for real-time performance and environmental data. Economic and operational considerations. While tidal energy has high upfront costs, its long-term benefits include predictable power output, low maintenance after installation, minimal fuel or operating costs. Government incentives, feed-in tariffs, and long-term power purchase agreements (PPAs) can enhance its economic viability. Parts summary. Tidal energy is a mature and dependable renewable energy source with significant potential in coastal regions worldwide. While the infrastructure can be capital-intensive, the predictability and sustainability of tidal power make it a critical component of future energy systems. With continuing technological advancements and environmental safeguards, tidal energy is poised to play a vital role in the global energy transition. Part 5. Wave energy, mechanisms and devices. Wave energy, derived from the surface motion of the ocean, is one of the most energy-dense forms of renewable power. Driven by wind blowing over vast ocean surfaces, waves can travel thousands of kilometers with little loss of energy. This part explores the principles behind wave energy, the technologies used to capture it, and the challenges in its development. Understanding wave energy. Waves are formed primarily by wind interacting with the surface of the ocean. The energy transferred from wind to water results in orbital motion of water particles. This motion can be harnessed to generate electricity. Key factors influencing wave energy. Wave height. Taller waves carry more energy. Wave period. Longer periods increase energy potential. Wavelength and speed affect the total power output. The power per meter of wave front is calculated using P equals rho G2H2T64 pi P equals 64 per G2H2T, where R equals water density, Gg equals gravitational acceleration, Hh equals wave height, Tt equals wave period. Types of wave energy devices. Wave energy devices are typically classified based on their orientation to waves and their method of energy extraction. Point absorbers. Floating devices that move up and down with the waves. Use hydraulic systems or linear generators to convert motion into electricity. Example, power buoy by Ocean Power Technologies. Pros. Simple design. Suitable for deep and shallow water. Cons. Must be moored securely. Sensitive to storm damage. Oscillating water columns, OWCs. traps a column of air above a column of water inside a chamber. Wave motion compresses and decompresses the air, driving a turbine. Example, Mutriku Power Plant, Spain. Pros: fixed to shore, easier maintenance. Double direction airflow increases efficiency. Cons: lower energy capture compared to offshore devices. C. Overtopping devices. Capture water as waves spill over into a reservoir. Stored water is released through low-head turbines. Pros: can generate power even after waves pass. High capacity potential. Cons: requires significant infrastructure. Affected by wave direction and height. D. Attenuators. Long multi-segment floating structures aligned parallel to wave direction. Hinges between segments flex as waves pass, generating electricity. Example, Palamas Wave Energy Converter, UK. Pros: effective in open ocean wave fields. Scalable design. Cons: complex mechanical systems. Susceptible to mechanical fatigue. E. Submerged pressure differential devices. Anchored to the seabed, sense pressure variations as waves pass above. Use membranes or hydraulic systems to generate power. Pros: hidden below surface, less visual impact. Protected from surface storms. Cons: requires strong anchoring. Suitable only in shallow waters. Deployment locations and considerations. Wave energy potential is highest in regions with strong and consistent winds over open oceans. Ideal locations include western coasts of continents, e.g., Portugal, Chile, Scotland, Australia. Islands and archipelagos, exposed to open ocean swells. Key site selection criteria: wave climate and sea state, water depth and seafloor conditions, proximity to grid infrastructure. Advantages of wave energy: high energy density compared to wind and solar. Predictable patterns in many regions. Small visual footprint, especially offshore devices. Complementarity with other renewable sources. Technical and environmental challenges. While promising, wave energy technologies face hurdles. Technical: mechanical complexity and survivability in harsh conditions. High costs for deployment, maintenance, and grid connection. Need for robust mooring and anchoring systems. Environmental: possible impact on marine ecosystems. Interference with navigation and fishing activities. Underwater noise and habitat disruption. Mitigation measures include environmental impact assessments, EIAs. Adaptive design to reduce ecological disturbance. Stakeholder engagement with local communities and industries. Notable projects and technologies. Mutriku OWC plant, Spain, one of the few operational grid-connected wave power plants. Carnegie Clean Energy, Australia, developing submerged devices integrated with desalination. WaveRoller, Finland, a bottom-hinged flap system in nearshore environments. Eco Wave Power, Israel, onshore system using breakwater structures. Innovation and the road ahead. Future developments in wave energy aim to improve device efficiency and durability through advanced materials. Cost-effectiveness via modular and scalable systems. Hybrid energy systems that combine wave, wind, and solar. Digital monitoring tools for predictive maintenance and performance optimization. Parts summary. Wave energy represents a vast, largely untapped renewable resource with the potential to significantly contribute to global energy needs. Though technical and environmental challenges remain, ongoing research and pilot projects continue to refine wave energy devices, bringing the sector closer to commercial viability. As technology advances, wave power is expected to become an integral component of coastal energy systems. Part 6. Ocean Thermal Energy Conversion (OTEC). Ocean Thermal Energy Conversion (OTEC) is a renewable energy technology that uses the temperature difference between warm surface seawater and cold deep seawater to generate electricity. This process is especially effective in tropical regions where the thermal gradient is sufficient year-round. OTEC offers a clean, sustainable, and continuous energy source, along with potential byproducts such as freshwater and cooling services. Principles of OTEC. OTEC systems exploit the thermal gradient between warm surface water, about 25 to 30 degrees Celsius, and cold deep sea water, 5 to 8 degrees Celsius, typically found at depths of 1,000 meters. The greater the temperature difference, the more efficient the system, although typical OTEC systems operate at low thermal efficiency, 2 to 5%, due to the small gradient. Types of OTEC systems. There are three primary types of OTEC systems. A. Closed-cycle OTEC. Uses a working fluid with a low boiling point, e.g., ammonia. Warm surface water heats the fluid, turning it into vapor to drive a turbine. Cold deep water condenses the vapor back into a liquid, repeating the cycle. Advantages. Stable and controlled environment. Ideal for electricity generation. Challenges. Potential leaks of the working fluid. Requires efficient heat exchangers. B. Open cycle OTEC. Uses seawater itself as the working fluid. Warm seawater is evaporated in a low-pressure environment, generating steam to drive a turbine. The steam is then condensed using cold deep seawater, often yielding desalinated freshwater. Advantages. Produces both electricity and potable water. No need for external working fluids. Challenges. Larger turbines needed due to low pressure. More complex system design. C. Hybrid cycle OTEC. Combines closed and open cycle systems. Uses an open cycle for steam production and a closed cycle for power generation. Advantages. Improves efficiency and water production. Flexible operation. Challenges. Technologically complex. Higher initial cost. Site requirements for OTEC. OTEC systems are best suited to regions with a temperature difference of at least 20 degrees Celsius between surface and deep waters. Tropical and equatorial oceans, e.g., Pacific Islands, Southeast Asia, Caribbean. Deep waters close to shore to reduce infrastructure costs. Stable wave and weather conditions. Key components of OTEC systems. Heat exchangers transfer thermal energy between seawater and working fluid. Turbines and generators convert thermal energy into mechanical and then electrical energy. Cold water pipe carries deep sea water to the surface, must be durable and flexible. Pumps move large volumes of seawater. Desalination units for open cycle convert condensed steam into freshwater. Benefits of OTEC. Baseload power can operate 24/7 unlike wind or solar. Renewable and sustainable, powered entirely by solar-heated ocean layers. Freshwater production, particularly valuable for island and coastal communities. Air conditioning and refrigeration, cold deep seawater can be used for cooling. Aquaculture support, nutrient-rich deep water can be used for marine farming. Challenges and limitations. Low thermal efficiency, requires large volumes of water to produce modest electricity. High capital costs, deepwater pipelines, corrosion-resistant materials, and offshore platforms are expensive. Technological complexity, requires sophisticated engineering to manage large-scale heat transfer. Environmental impact, discharge of cold water can affect marine ecosystems and local currents. Notable OTEC projects. NELHA, Hawaii, USA. The Natural Energy Laboratory of Hawaii Authority has hosted several OTEC demonstrations. Focus on research and small-scale desalination. B. Kumejima OTEC Plant, Japan. Operational pilot plant generating 100 kilowatts. Supplies electricity and supports aquaculture and agriculture. C. Indian OTEC initiatives. India's National Institute of Ocean Technology, NIOT, is planning floating OTEC plants near Lakshadweep Islands. The future of OTEC. Advances in materials science, thermodynamics, and offshore construction are helping OTEC become more feasible. Trends shaping the future of OTEC include modular floating platforms for easier deployment, integration with other renewables, e.g. solar, wind, use in remote or off-grid areas, especially small island nations, development of deep ocean resource hubs combining energy, desalination, and aquaculture. Parts summary. OTEC is a promising but underdeveloped ocean energy technology that can offer clean electricity and freshwater to tropical coastal and island regions. Though the technology faces efficiency and cost challenges, its potential for continuous, sustainable power makes it an important avenue for future energy systems. As innovation progresses, OTEC may become a cornerstone of energy strategies in equatorial regions. Part 7. Salinity Gradient Energy and Emerging Technologies. Salinity gradient energy, also known as blue energy, is derived from the chemical potential between saltwater and freshwater. This form of ocean energy taps into the natural osmotic pressure differences that occur where rivers meet the sea, estuaries. Though still in the experimental or early commercial phases, salinity gradient energy and other emerging marine technologies offer promising prospects for renewable power generation, especially in coastal and riverine regions. Fundamentals of salinity gradient energy. When freshwater and saltwater mix, energy is released due to the difference in salt concentration. This gradient creates an osmotic pressure that can be harnessed to generate electricity. Osmotic pressure is the force that moves water from areas of low to high solute concentration. The theoretical potential of salinity gradient energy is about 0.7 to 1.0 megawatts per cubic meter of freshwater mixing with seawater. Global potential, an estimated 2,000 terawatt-hours per year, comparable to about 15% of current global electricity demand. Technologies for salinity gradient energy. Several technologies aim to harness this energy through different physical or chemical processes. A. Pressure-retarded osmosis, PRO. Freshwater and seawater are separated by a semi-permeable membrane. Water from the freshwater side flows into the saltwater side, increasing pressure. This pressure drives a turbine to generate electricity. Advantages. Proven concept with significant research backing. Can be integrated into existing desalination plants. Challenges. Membrane fouling and efficiency loss over time. High cost of membrane materials. B. Reverse electrodialysis, RED. Alternating cation and anion exchange membranes are placed between saltwater and freshwater. Ions migrate through the membranes, creating an electrical potential. Advantages. Higher efficiency at low flow rates. Modular and scalable systems. Challenges. Requires highly selective and durable membranes. Still in development for large-scale deployment. C. Capacitive mixing, CapMix. Uses the electrochemical potential generated by alternating fresh and saltwater across electrodes. The difference in ionic concentration generates electricity through charge and discharge cycles. Advantages. No need for membranes. Simpler design. Challenges. Limited energy output. Early stage development. 7.3 Site suitability for salinity gradient systems. Ideal locations for salinity gradient energy. River estuaries. deltas with consistent freshwater outflows, areas with existing water infrastructure, e.g. desalination plants. Examples include the Netherlands, IJsselmeer and North Sea, Amazon and Congo River deltas, Ganges-Brahmaputra Delta in South Asia. Environmental and technical considerations. Environmental: minimal emissions or habitat disruption compared to tidal barrages. Potential impacts from brine discharge or membrane cleaning chemicals. Technical: need for anti-fouling long-lasting membranes. Maintenance of water quality and salinity differential. Integration with coastal energy and water systems. Key projects and developments. Statkraft Norway built the world's first osmotic power prototype plant. Demonstrated feasibility, but faced challenges in membrane efficiency. Redstack, Netherlands. Pilot red plant in Afsluitdijk, a dam separating fresh and salt water. Focus on optimizing stack design and membrane materials. Pro-based desalination hybrids. Research in Japan, Korea, and Israel on integrating pro with desalination to recover energy from brine discharge. Emerging marine energy technologies. Beyond salinity gradient systems, other marine energy innovations include ocean currents. Harnessing consistent underwater currents like the Gulf Stream. Similar to tidal stream turbines, but in deeper water. Marine biomass. Seaweed and algae cultivated for biofuels or biogas. Can be co-located with marine energy farms. Hydrothermal vent systems. Experimental concepts utilizing the geothermal heat and mineral-rich fluids from ocean floor vents. Floating wind solar hybrid platforms. Combine solar PV, wind turbines, and wave devices on shared offshore platforms. Future outlook and integration. Hybrid systems combining wave, wind, and salinity gradient energy can offer synergistic benefits. Microgrids and island systems can especially benefit from salinity gradient energy. Advancements in nanomaterials and membrane science will enhance efficiency and reduce costs. Policy and funding support are critical to transitioning from pilot to commercial scale. Parts summary. Salinity gradient energy is a promising but underutilized resource with the potential to contribute significantly to sustainable energy generation in coastal regions. With the right technology, particularly in membrane design and energy recovery systems, this clean and continuous energy form could complement other marine and renewable sources. As research and pilot projects continue to demonstrate feasibility, blue energy could play a vital role in the next generation of renewable energy infrastructure. Part 8. Environmental impacts of ocean energy systems. Ocean energy systems, including tidal, wave, ocean thermal, and salinity gradient technologies, offer significant benefits in the fight against climate change. However, like all energy infrastructure, they interact with the surrounding environment. Understanding and mitigating their ecological impacts is essential to ensure sustainable deployment. This part explores the potential environmental effects of ocean energy technologies, the mechanisms of impact, and strategies to minimize harm. Overview of environmental considerations. Ocean energy projects can impact the marine environment in several ways, such as physical disturbance of seabed and habitat, alteration of hydrodynamics and sediment transport, noise generation affecting marine life, electromagnetic field emissions from underwater cables, risks of pollution or leakage from equipment. The scale and type of impact depend on the technology, location, and design of the system. Impacts on marine ecosystems. Benthos and seafloor habitats. Installation of underwater infrastructure can disturb benthic, bottom-dwelling organisms. Anchoring pipelines and foundations may damage coral reefs, seagrass beds, or soft sediments. Changes in sedimentation patterns may affect habitats. Mitigation. Site projects away from ecologically sensitive zones. Use minimally invasive anchoring techniques. Monitor sediment shifts and adjust designs accordingly. B. Marine mammals and fish. Underwater turbines and moving parts can pose collision risks. Noise and vibrations may disrupt communication, navigation, and migration. Mitigation. Employ acoustic deterrent devices. Design rotor blades to minimize harm. Schedule construction to avoid sensitive breeding or migration seasons. C. Birds and surface-dwelling species. Offshore platforms may attract birds, but can also increase collision or entrapment risks. Floating devices could impact sea turtles and other surface species. Mitigation. Avoid key nesting or migration areas. Design visible structures with deterrents. 8.3 Hydrodynamic and geomorphological changes. A. Tidal energy systems. May alter natural water flow, impacting estuaries and wetlands. Can change tidal amplitude and flow direction, affecting sediment movement. B. Wave and current devices. Could reduce wave heights and current speeds, altering sediment transport and coastal erosion patterns. Mitigation. Model hydrodynamic impacts pre-construction. Optimize device layout to preserve natural flow regimes. Chemical and thermal pollution. A. Closed-cycle OTEC systems. Discharge of cold, nutrient-rich water can affect surface ecosystems. May create localized zones of altered temperature and chemistry. B. Leaks and discharges. Risk of oil or hydraulic fluid leaks from mechanical systems. Open-cycle systems must manage biofouling and anti-fouling chemical use. Mitigation. Use non-toxic working fluids and biodegradable lubricants. Employ closed-loop fluid systems where possible. Electromagnetic fields, EMFs. Subsea cables and electrical equipment generate EMFs that may interfere with navigation in species like sharks, rays, and eels. Behavior in migratory fish sensitive to electric and magnetic fields. Mitigation. Shield cables to reduce EMF emissions. Bury cables beneath the seabed. Cumulative and synergistic impacts. In regions with multiple ocean energy systems or other marine activities, shipping, fishing, aquaculture. Cumulative impacts may amplify ecological stress. Synergistic interactions can affect biodiversity and water quality. Mitigation. Conduct strategic environmental assessments, SEAS. Engage stakeholders in marine spatial planning. Promote integrated coastal zone management. Environmental monitoring and adaptive management. Best practices for ensuring sustainability. Baseline studies to understand pre-installation conditions. Continuous monitoring of noise, species abundance, water quality, etc. Adaptive management to allow system modifications in response to findings. Tools used. Acoustic monitoring. Underwater video surveillance. Remote sensing and drone technologies. Regulatory frameworks and guidelines. Several international and national frameworks guide environmental assessments of ocean energy. United Nations Convention on the Law of the Sea, UNCLOS. Environmental Impact Assessment, EIA regulations. Marine Strategy Framework Directive, EU. Local and regional permitting processes. Encouragement of public participation and transparency is key to successful and socially accepted deployment. Positive environmental contributions. Despite potential risks, ocean energy systems can offer environmental co-benefits. Artificial reef effect. Structures may support marine life colonization. Climate mitigation. Reduction of greenhouse gas emissions. Desalination and nutrient upwelling. Beneficial for arid or nutrient-poor zones. Marine protection zones. Energy installations can act as de facto no-fishing zones. Parts summary. While ocean energy systems present some environmental risks, careful site selection, thoughtful design, rigorous environmental assessments, and active management can significantly reduce negative impacts. Moreover, when integrated thoughtfully, these technologies can offer ecological co-benefits. Sustainable expansion of ocean energy requires a holistic approach that balances technological innovation with environmental stewardship and community involvement. Part 9. Economic viability and market potential of ocean energy. Ocean energy technologies, though still emerging, have the potential to play a critical role in the global transition to renewable energy. However, their widespread adoption hinges on their economic competitiveness, investment attractiveness, and market scalability. This part evaluates the economic aspects of ocean energy systems, including costs, financing, market dynamics, and pathways to commercialization. Economic characteristics of ocean energy. Ocean energy projects involve both high capital expenditure, CapEx, and moderate operational expenditure, OpEx. Key economic considerations include high upfront costs for technology development, infrastructure, and marine installation. Moderate maintenance costs due to harsh marine environments. Long lifespan of infrastructure, 20 to 30 years, offering stable returns if maintained properly. Revenue generation through electricity sales, freshwater, cooling, or carbon credits. Cost breakdown by technology. Note: LCOE values vary based on location, scale, and technology type. Factors affecting cost and viability. Site conditions, depth, seabed characteristics, and wave tidal intensity affect design and cost. Infrastructure. Proximity to grid connection and ports reduces logistical challenges. Scale. Larger installations benefit from economies of scale. Technology maturity. More mature technologies like tidal barrage are closer to commercial viability. Policy support. Subsidies, feed-in tariffs, and carbon pricing improve financial feasibility. Financing ocean energy projects. Securing investment for ocean energy involves managing high risk and uncertain returns. Financing models include public funding and grants, government R&D and pilot project support, private equity and venture capital for startups and technology developers, green bonds and climate finance for projects aligning with sustainability goals, power purchase agreements (PPAs), long-term contracts with utilities or corporations, risk mitigation strategies, technology insurance, revenue guarantees, public-private partnerships (PPPs), market potential by region. A. Europe. Leading in wave and tidal energy development. Countries like the UK, France, and Norway have advanced demonstration projects. Supportive EU frameworks, e.g. Horizon Europe, Blue Energy programs. B. Asia Pacific. Strong interest in OTEC and tidal energy, Japan, South Korea, India, China. Island nations exploring ocean energy for energy security and desalination. C. North America. Canada. Focus on Bay of Fundy tidal stream projects. USA. DOE support for wave energy R&D on Pacific and Atlantic coasts. D. Small island developing states SIDS. High potential due to isolation, high electricity costs, and abundant ocean resources. OTEC and wave energy are attractive for energy and water needs. Revenue streams beyond electricity. Freshwater production from OTEC and open-cycle systems. Cooling services using deep-sea water, air conditioning, cold storage. Carbon credits for emissions reductions. Tourism and educational outreach from demonstration sites. Marine aquaculture supported by nutrient-rich, upwelling water. Barriers to commercialization. High upfront capital costs and long payback periods. Grid integration challenges in remote or offshore locations. Technological uncertainty and lack of performance data. Limited regulatory frameworks, tailored to marine energy, environmental permitting delays, and community concerns. Strategies to improve economic viability. Innovation in materials and design to reduce costs. Standardization and modularization of components. Demonstration and pilot projects to de-risk investments. Incentives and subsidies to bridge the commercialization gap. Cross-sector collaboration with shipping, aquaculture, and offshore wind. Future market outlook. The ocean energy market is expected to grow significantly by 2030 and beyond, driven by climate commitments and carbon neutrality targets, rising energy demand in coastal regions, technological convergence and hybrid platforms, increased investments in blue economy initiatives. Estimates suggest the global ocean energy market could exceed $30 billion by 2040, contingent upon supportive policy and innovation breakthroughs. Parts summary. While ocean energy currently faces economic and technical challenges, it holds substantial market potential, especially for coastal and island regions. Cost reductions through technological innovation, coupled with targeted financing and supportive policy, are key to unlocking its viability. As part of a diversified renewable portfolio, ocean energy could provide stable, sustainable, and multifunctional energy solutions for the future. Part 10. Policy, Regulation, and International Cooperation in Ocean Energy Development. The successful deployment of ocean energy technologies relies not only on technical and economic factors, but also on robust policy frameworks, clear regulatory processes, and international collaboration. Because ocean energy systems operate in marine environments governed by complex jurisdictional laws, supportive governance structures are crucial. This part explores the role of policy, regulation, and global cooperation in advancing ocean and tidal energy. Role of policy in ocean energy development. Policies serve as catalysts for innovation and investment in ocean energy. Key policy goals include reducing greenhouse gas emissions, enhancing energy security and diversification, supporting technological innovation, promoting coastal and island resilience, policy instruments supporting ocean energy, feed-in tariffs and contracts for difference (CFDs) for price certainty, research and development (R&D) grants for technology advancement, tax incentives and rebates for developers and investors, renewable energy targets or mandates that include marine energy, regulatory frameworks for marine energy projects. Because ocean energy systems operate in the marine environment, they are subject to a combination of national, regional, and international regulations. A. Permitting and licensing. Site selection, environmental assessments, and stakeholder consultations are required before project approval. Agencies typically involved include energy, environment, and maritime authorities. Regulatory clarity and streamlined processes can reduce project delays. B. Marine spatial planning (MSP). Integrates ocean energy into broader ocean use, such as fishing, navigation, and conservation. Helps avoid conflicts and ensures responsible ocean stewardship. C. Environmental impact assessments (EIAs). Required for most large-scale projects to evaluate effects on marine ecosystems. Must include monitoring and mitigation plans. D. Grid access and interconnection. Policies must ensure fair access to transmission networks and prioritize renewable integration. National strategies and examples. United Kingdom. Leading nation in wave and tidal energy. Marine Energy Council and contracts for difference (CFD) scheme support development. Established Marine Management Organization for permitting. European Union. Strong policy framework under the European Green Deal and Blue Economy Strategy. Horizon Europe funds R&D in marine renewables. Ocean Energy Europe (OEE) coordinates industry interests. United States Department of Energy, DOE, supports marine energy through the Water Power Technologies Office. Regional testing centers like the Pacific Marine Energy Center, PMEC. Federal Energy Regulatory Commission, FERC, handles project licensing. Canada focused on tidal energy in Nova Scotia and British Columbia. Feed-in tariffs and Marine Renewable Energy Act support development. Small island states. Nations like Fiji, Mauritius, and the Maldives include ocean energy in nationally determined contributions, NDCs, under the Paris Agreement. Support from international donors and climate finance mechanisms. International cooperation and agreements. A United Nations Convention on the Law of the Sea, UNCLOS, provides the legal framework for marine energy development beyond national waters. Defines exclusive economic zones, EEZs, and responsibilities of coastal states. B. International Renewable Energy Agency, IRENA, promotes global cooperation in renewable energy, including ocean energy. Provides data, policy guidance, and technical support. C. Ocean Energy Systems, OES, by the IEA. Multinational initiative that facilitates research, information sharing, and collaborative projects in ocean energy. D. Mission Innovation. International partnership focused on clean energy innovation, including marine technologies. Role of climate and blue economy policies. Ocean energy is increasingly seen as a contributor to climate change mitigation by reducing fossil fuel dependence. Climate adaptation for coastal resilience and freshwater supply. Blue economy development, which emphasizes sustainable use of ocean resources for economic growth. Many governments are embedding ocean energy within their national energy plans. Maritime spatial strategies. Sustainable Development Goals, SDGs, particularly 7 Sudanese pounds affordable and clean energy, and 14 Sudanese pounds, life below water. Challenges in policy and governance. Despite growing interest, several challenges persist. Policy fragmentation and lack of coordination across jurisdictions. Lengthy and complex permitting processes. Inadequate support mechanisms for emerging technologies. Limited awareness and stakeholder engagement. Recommendations for effective governance. To enhance policy and regulatory support. Harmonize permitting procedures across agencies. Develop marine-specific renewable energy targets. Provide risk-sharing instruments for developers, e.g., guarantees, insurance. Invest in capacity building for regulatory bodies and stakeholders. Encourage international data sharing and best practices. Parts Summary. Sound policy and regulatory frameworks are essential for scaling up ocean energy. They provide clarity, reduce risks, and ensure that projects are environmentally and socially responsible. International collaboration, streamlined governance, and alignment with climate and blue economy goals can accelerate the global uptake of ocean and tidal energy, unlocking their full potential for a sustainable future. Part 11. Integration of ocean energy into the power grid and hybrid systems. Ocean energy technologies have the potential to contribute significantly to a low-carbon energy future, especially in coastal and island regions. However, integrating ocean energy into existing power grids presents technical, economic, and regulatory challenges. This part explores the integration of ocean energy into power systems, the use of hybrid configurations, and the role of storage and smart grids in optimizing performance. Overview of power grid integration. Integrating ocean energy into the grid involves connecting variable and sometimes remote sources of generation to national or regional electricity networks. Key considerations include grid availability and proximity to the generation site, Power variability due to changing tides and wave patterns. Compatibility with existing grid infrastructure and regulations. Power quality and reliability to meet demand and ensure system stability. Characteristics of ocean energy supply. Ocean energy systems generally produce predictable but intermittent power. Tidal energy is highly predictable, driven by lunar cycles. Wave energy is less predictable, but still offers some forecasting advantages over wind or solar. OTEC and salinity gradient systems can provide near-continuous baseload power. Understanding these supply profiles helps utilities plan grid integration more effectively. Grid connection technologies and infrastructure. To transmit ocean-generated power to the grid, the following components are used. Subsea power cables to carry electricity to shore. Offshore substations to collect and condition power from multiple devices. Transformers and converters to adjust voltage and frequency. Onshore grid interconnection points, often located in remote or coastal regions. Challenges. High cost of submarine cables. Technical difficulties in harsh marine environments. Energy losses during transmission. Hybrid renewable energy systems. Hybrid systems combine ocean energy with other renewable sources to enhance reliability and utilization. Common hybrid configurations include ocean plus wind. Offshore wind and tidal energy complement each other seasonally and daily. Shared infrastructure reduces cost, e.g. joint substations, cabling, platforms. B. Ocean plus solar. Ideal for island nations and coastal microgrids. Solar covers daytime peaks, while tidal and wave energy provide nighttime or continuous power. C. Ocean plus diesel or biomass. Hybrid systems can use diesel generators or biomass as backup for remote off-grid locations. Reduces fuel dependency and emissions. Role of energy storage. Energy storage systems, help balance the intermittent nature of ocean energy. Storage options include batteries, e.g. lithium-ion flow batteries, useful for short-term balancing. Pumped hydro, stores energy by moving water to elevated reservoirs. Hydrogen production via electrolysis enables long-term storage and fuel flexibility. Flywheels and supercapacitors, for grid frequency regulation and rapid response. Benefits. Smoothens output fluctuations. Enhances grid stability. Enables time shifting of energy to match demand peaks. Smart grids and digitalization. Smart grid technologies support ocean energy integration by enabling real-time monitoring and control of distributed energy systems. Forecasting tools for tidal and wave conditions to plan energy dispatch. Demand response systems to align consumption with generation. Microgrids in island or remote regions with integrated control of hybrid resources. Digitalization improves efficiency, reduces costs, and enhances system resilience. Integration in island and remote communities. Ocean energy holds particular promise for islands and isolated communities where diesel dependency is high. Grid access is limited or non-existent. Renewable resources are abundant. Case studies. Tokelau, exploring wave energy to supplement solar. Orkney Islands, UK, integrated tidal energy with hydrogen production and smart grid technologies. Hawaii, USA, research into OTEC and wave energy for long-term energy independence. Regulatory and economic considerations. Grid codes must be updated to accommodate marine energy technologies. Tariffs and incentives for grid connection and storage use need to be clarified. Ownership models such as community-based microgrids can enhance local acceptance. Public and private utilities should collaborate to create flexible and inclusive energy systems that incorporate ocean energy. Future outlook for ocean energy integration. Advancements that will support better integration include dynamic cable systems with longer lifespans, modular offshore substations, eye-driven forecasting for waves and tides, integrated offshore platforms that host wind, wave, solar, and aquaculture. A future of multi-use marine spaces powered by hybrid, resilient, and intelligent energy systems is within reach. Parts summary. Integrating ocean energy into the power grid is both a technical and strategic challenge, requiring innovations in infrastructure, storage, and smart technologies. Hybrid systems and microgrids offer promising pathways, especially for islands and coastal regions. As digitalization, energy storage, and offshore infrastructure advance, ocean energy will play an increasingly important role in resilient, low-carbon energy systems. Part 12. Case Studies and Real-World Applications of Ocean and Tidal Energy. The practical implementation of ocean and tidal energy technologies provides critical insight into their technical performance, environmental interactions, economic viability, and social acceptance. This part highlights notable case studies from around the world, showcasing different ocean energy technologies in action, the lessons learned, and their contribution to the renewable energy landscape. United Kingdom, Maygen Tidal Energy Project, Scotland. Technology, Tidal Stream Developer, SIMEC Atlantis Energy, location, Pentland Firth, Scotland. Key features. World's largest planned tidal stream project. Currently operating with 6 megawatts capacity, planned expansion to 398 megawatts. Turbines installed on the seabed to harness fast tidal currents. Outcomes. Demonstrated reliable, predictable energy generation. Valuable data collected for environmental and performance analysis. Supported local job creation and technology export. France, Lorentz Tidal Barrage. Technology, Tidal Barrage Developer EDF Électricité de France, location Rance River, Brittany. Key features. Operational since 1966, 240 megawatts capacity. Uses a dam-like structure to trap and release tidal waters. Outcomes. One of the oldest and most successful ocean energy projects. Still economically viable, after over 50 years. Serves as a model for evaluating environmental impacts of large-scale tidal infrastructure. Portugal, Agucadora Wave Farm Pilot Project. Technology, Wave Energy Developer, Enersys and Palamas Wave Power, location, off the coast of northern Portugal. Key features. World's first commercial wave farm, launched in 2008. Used Palamas attenuator-type devices. Outcomes. Early commercial demonstration of wave power. Faced technical and financial challenges. Provided important lessons for next-generation wave technologies. South Korea, Siwa Lake Tidal Power Station. Technology, Tidal Barrage Developer, Korea Water Resources Corporation, location, Gyeonggi Province, South Korea. Key features. World's largest tidal power plant, 254 megawatts. Built into an existing seawall to minimize cost and environmental impact. Outcomes. Generates power for over 500,000 people. Also aids in water quality management. Highlights the potential for integrating tidal energy with existing infrastructure. Canada Force, Bay of Fundy Tidal Demonstration. Technology, Tidal Stream Developer, Fundy Ocean Research Center for Energy Force, location, Bay of Fundy, Nova Scotia. Key features. Site of some of the strongest tides in the world. Test bed for multiple tidal technologies, including turbines from various developers. Outcomes. Supports environmental monitoring and community engagement. Facilitates innovation in device design and grid integration. Helps Canada advance marine renewable policies. Japan, Kumejima Ocean Thermal Energy Conversion, OTEC. Technology, OTEC Developer, Saga University and Local Government, location, Okinawa Prefecture, Japan. Key features: pilot-scale OTEC plant producing electricity and fresh water. Uses temperature difference between surface and deep ocean water. Outcomes: demonstrated dual benefits, energy generation and desalination. Potential to serve remote islands. Supports Japan's energy diversification strategy. India, tidal power pilot projects. Technology: Tidal proposed and pilot location, Gulf of Kutch and Gulf of Khambhat, Gujarat. Key features: high tidal ranges identified in western coastal regions. Government and private feasibility studies conducted. Outcomes: project plans stalled due to high costs and regulatory hurdles. Studies continue to assess hybrid and low-impact alternatives. Highlights the need for supportive policies and risk mitigation. United States, Pacific Marine Energy Center, PMEC. Technology: wave and tidal, research and testing developer. Oregon State University and partners, location, Oregon coast and Alaska. Key features: National Marine Energy Testing Facility. Supports development of wave energy converters. Outcomes: accelerates U.S. marine energy innovation. Provides data on performance, durability and environmental effects. Builds collaboration between academia, industry and government. Mauritius, blue economy and ocean energy exploration. Technology: wave and OTEC, exploratory stage developer, Government of Mauritius and international partners, location, Indian Ocean. Key features: national plan to integrate ocean energy into its blue economy strategy. Focus on energy security and climate resilience. Outcomes: capacity building and international technical assistance underway. Exploration of desalination and cooling applications. Emphasizes the role of ocean energy for small island developing states, SIDS. Lessons learned from real-world applications. Technology adaptation. Marine environments demand robust, corrosion-resistant and modular systems. Environmental monitoring. Long-term data is essential to understand ecosystem impacts. Community engagement. Local involvement ensures project acceptance and social license. Financial support. Subsidies, grants, and pilot funding are crucial in early stages. Policy frameworks. Clear, supportive regulations accelerate deployment. Parts summary. Real-world ocean and tidal energy projects offer valuable insights into the opportunities and challenges of marine renewables. From early tidal barrage systems to advanced hybrid and research platforms, these case studies underscore the growing maturity of ocean energy technologies. With continued innovation, investment, and policy support, ocean energy can become a mainstream component of the global clean energy mix. Part 13: Future Trends and Innovations in Ocean and Tidal Energy. As the world accelerates its transition towards sustainable and low-carbon energy systems, ocean and tidal energy technologies are poised to play a more significant role. This part explores the emerging trends, technological innovations, and research frontiers shaping the future of marine energy. It also outlines the strategic steps necessary to realize the full potential of ocean and tidal power in the coming decades. Advancements in device design and efficiency. Continuous innovation in technology is essential to improve the performance and reduce the cost of ocean energy systems. Modular and scalable designs. Next-gen devices are increasingly modular, allowing for scalable deployments. Easier installation, maintenance, and adaptability to different marine conditions. Improved turbine designs. Vertical axis and bidirectional tidal turbines for better efficiency in variable flows. Enhanced blade materials and geometries for reduced wear and drag. Bio-inspired technologies. Designs mimicking marine animals, e.g., stingrays, jellyfish, for more efficient energy capture. Flexible and responsive structures better suited for harsh ocean dynamics. Integration with multi-use offshore platforms. Future ocean energy systems will likely be integrated into multi-use marine platforms, which combine various activities such as offshore wind and wave energy production, aquaculture and seaweed farming, desalination and ocean observation systems. These hybrid platforms reduce costs by sharing infrastructure, e.g., moorings, substations, and increasing resource efficiency. Advanced materials and durability. Material science plays a pivotal role in extending device life and reducing costs. Corrosion-resistant composites and self-healing coatings. Smart materials that adapt to environmental changes and reduce fatigue. Additive manufacturing, 3D printing, for rapid prototyping and customized components. Digitalization and artificial intelligence, AI. AI and digital technologies are transforming how ocean energy systems are designed, operated, and maintained. AI-driven forecasting models for waves, tides, and energy production. Digital twins to simulate device performance and predict failures. Autonomous underwater vehicles, AUVs, for inspection, repair, and monitoring. Smart grids and IoT systems will optimize energy dispatch and ensure efficient grid integration. Energy storage and hydrogen integration. As ocean energy becomes more prominent, coupling it with advanced storage solutions is key. Marine-based battery systems for short-term storage. Hydrogen production through electrolysis using ocean energy. Enables green hydrogen generation in coastal or offshore settings. Hydrogen can be stored, transported, or used for fuel cells. This synergy helps manage variability and opens pathways to decarbonize hard-to-abate sectors. Floating and deep water technologies. Floating platforms are unlocking access to deeper ocean areas with stronger and more consistent energy resources. Floating tidal and wave energy systems can operate farther offshore. Dynamic mooring systems provide flexibility and resilience in deep waters. Opens opportunities for energy generation near remote islands and shipping routes. Environmental innovations and co-benefits. Sustainable ocean energy development includes technologies that enhance marine ecosystem health. Eco-engineered foundations that serve as artificial reefs. Low-noise turbines to reduce impacts on marine mammals. Monitoring platforms to track biodiversity and water quality. Co-benefits like habitat creation, fishery enhancement, and ocean data collection are gaining attention. Policy and market evolution. Forward-looking policies and financial instruments are shaping the future. Blue bonds and green financing tailored to marine renewables. Carbon pricing mechanisms that favor clean ocean energy. International standards and certifications for safety, performance, and sustainability. Governments and investors are increasingly integrating ocean energy into climate action plans and green growth strategies. Global collaboration and knowledge sharing. The future of ocean and tidal energy will be driven by global partnerships. Open-source technology platforms to accelerate innovation. Cross-border R&D programs and shared testing facilities. Capacity building in developing and island nations to ensure inclusive energy transitions. Initiatives like Ocean Energy Systems, OES, IRENA, and Mission Innovation will continue to foster collaborative progress. Vision for the future. By 2050, ocean and tidal energy could become mainstream components of the global energy mix, characterized by high-efficiency, autonomous marine power systems. Integrated ocean energy farms combining wind, wave, solar, and aquaculture. Resilient coastal energy hubs powering islands, ports, and smart cities. Major contributions to net zero emissions, energy security, and blue economy development. Parts summary. The future of ocean and tidal energy is filled with promise and innovation. As technological breakthroughs, digital tools, and sustainable practices evolve, ocean energy will transition from niche applications to widespread deployment. Embracing these trends will not only transform energy systems, but also foster a more resilient and regenerative relationship with our oceans. Part 14: Conclusion and Recommendations. Ocean and tidal energy represent one of the most promising frontiers in the renewable energy landscape. As nations strive to meet climate goals, reduce dependence on fossil fuels, and enhance energy resilience, harnessing the vast untapped power of the oceans becomes both a necessity and an opportunity. This concluding part synthesizes key insights from the course and offers actionable recommendations for stakeholders involved in the advancement of ocean and tidal energy. Summary of key insights. Abundant and predictable resource. Ocean energy, especially tidal, offers predictable and consistent energy generation. Vast potential exists globally, particularly in coastal and island regions. Technological diversity. A wide array of technologies, tidal stream, tidal range, wave energy, OTEC, and salinity gradient can cater to varied geographies and needs. Environmental and socioeconomic benefits. Ocean energy contributes to low-emission power, supports blue economy development, and can be designed with minimal ecological disruption. Challenges in deployment. High initial costs, technological complexity, harsh marine conditions, and regulatory uncertainty remain barriers to large-scale implementation. Growing momentum. Several successful pilot and commercial projects worldwide demonstrate technical viability. Integration with smart grids, hybrid systems, and storage is improving performance and reliability. Strategic recommendations. For policymakers and governments. Develop clear regulatory frameworks specific to marine renewable energy. Incentivize early-stage projects through feed-in tariffs, grants, and tax benefits. Integrate ocean energy into national energy and climate plans. Support marine spatial planning to balance ocean uses while promoting renewables. For industry and developers. Focus on scalable, modular, and low-maintenance technologies. Invest in long-term environmental monitoring to build public trust and improve designs. Pursue hybrid solutions that combine ocean energy with solar, wind, or hydrogen production. Adopt open innovation models to reduce duplication and accelerate deployment. For researchers and academia. Expand R&D on materials science, biofouling resistance, and advanced mooring systems. Explore digital twin modeling, AI, and machine learning for system optimization. Collaborate globally to pool data, share lessons, and standardize methodologies. For communities and civil society. Engage early and transparently with affected communities. Develop co-ownership models for local benefit and empowerment. Educate the public about the advantages and limitations of ocean energy. The role of ocean energy in climate action. Ocean and tidal energy can make vital contributions to reducing greenhouse gas emissions, enhancing energy access and equity, building resilient infrastructure in vulnerable regions, promoting sustainable development through blue economy synergies. Their inclusion in global and regional climate strategies, such as nationally determined contributions, NDCs, can strengthen overall progress toward the Paris Agreement goals. Looking ahead. As the global energy transition gains pace, ocean energy must evolve from experimentation to commercialization. Strategic partnerships, inclusive governance, and technological innovation will be the pillars of this evolution. By 2050, ocean energy could supply a significant portion of global electricity needs, empower island nations to achieve energy independence, serve as a foundation for climate-resilient, sustainable coastal development. The ocean, once seen solely as a resource for transport and food, is now recognized as a powerful source of clean, renewable energy. Harnessing this energy responsibly and effectively is not only an environmental imperative, but also an economic and social opportunity for the future. Final thoughts. The tides rise and fall with a rhythm as old as the earth. Waves crash on shores with unwavering persistence. These forces, constant, immense, and often overlooked, carry with them the promise of a cleaner, brighter energy future. The time to invest in ocean and tidal energy is now. With vision, commitment, and collaboration, we can turn the energy of the oceans into a legacy of sustainability for generations to come.